Morning, everyone. My name is Renyuan Liu. I'm from George Mason University, and my advisor is Professor Shuochao. It's my pleasure to share our work DAF today, and it's a group work of George Mason University, JPMorgan, and University of Kansas. For the on-device training, one of the biggest challenge, especially on edge and mobile platforms, is the limited memory capacity. We can see from the figure that the largest portion of memory consumption during training comes from the activations. Dynamic quantization is a promising approach to compress activations, where each activation tensor is adaptively compressed based on its importance. However, most of dynamic quantization methods focus only on the theoretical feasibility of quantization. Very few of them actually implement and evaluate how such compression would work in a real system. For example, some AI work attempts to represent the float 16 tensor in a lower precision format, such as U⁴. This typically computes the quantized values and analyze how the reduced numerical range affects model accuracy, thereby estimating the potential compression ratio in theory. But they just stored the quantized U⁴ values using the original 16 bits, which means that they cannot achieve true memory savings. In contrast, our goal is to realize those dynamic quantization with real memory compression in system level. However, in real-world systems, applying dynamic quantization introduces several practical challenges. First is the extra computation overhead. Additional kernels are required for the quantization and the dequantization, which can slow down executions. The second is the packing and the data layout issues. Activations must be carefully packed and unpacked to ensure efficient storage and computation. Third, memory fragmentation. Frequent storing and discarding of activations can cause fragmentation, reducing effective memory savings. To address these issues, we propose DAF. It's a system that optimizes the quantized pipeline, leverages collaborative CPU-GPU execution, and introduces a memory management system. This design effectively improves performance and enables practical deployment on memory-constrained devices. So let's go to the details. In standard training, during the forward pass, each layer computes output for the next layer and then stores its input as an activation. During the backward pass, these activations are used to compute gradients. To quantize activations, we need the reduction statistics, like the mean and max value of each tensor. However, computing these values efficiently on a GPU is non-trivial. This is because GPUs are good at splitting the work across many outputs, so they can compute the outputs in parallel. In contrast, a reduction operation yields only one output, the mean or the max, and the traditional approach typically relies on a single thread to iterate over all elements of the tensor, resulting in high latency. Here, we use a fused GPU kernel to solve the problem. While doing the forward computation, we add a collective reduction operation to get the required values of the output. The key idea here is to take advantage of the hierarchical structure of the GPU by breaking the reduction process into two parts, a parallel operation and an atomic operation. This design maximizes GPU parallelism, and by fusing the kernel, also reduces the number of memory accesses. Here is the example. To get a reduction result of a tensor, such as find a mean value, we first divide the input data and read them into registers parallelly. Then each thread writes its mean value to shared memory. And now we do a parallel reduction on shared memory to find the mean value of each GPU block. At each step, threads compile piles of values and write the smaller one to the front position. After logging steps, the minimum value ends up at the beginning of the list. Finally, we use an atomic operation to store the minimum value in DRAM. The whole approach avoids the limitation of traditional GPU kernels, which typically relies on a single thread for reduction, as we said, and it also reduces the number of DRAM accesses, thereby improving efficiency. Second, when storing quantization activations, we want to pack them efficiently. We leverage the unified memory on SoCs. While the GPU performs forward computation, the CPU handles layout transformations in parallel. For backward computation, either the CPU or GPU can do the unpack things, depending on the hardware speed. Since the quantized data is much smaller than the full precision data, so GPU unpacking is often efficient enough to do that. The layout transformation kernel involves three main challenges that we address. First, let's say the quantized value is 5 and is supposed to be stored as U in 4. In existing dynamic quantization methods, this is just fake quantization. The value still ends up in float 16. What we want to do is to store it in real U in 4. But that leads to a problem, that is how to convert the data types efficiently. The original bit conversion instructions usually have much slower throughput than regular computation, sometimes up to 8 times slower. To tackle this, we use a computation-based method instead of relying on traditional instructions. Specifically, we apply a fixed mask and a predefined constant to perform the conversion. Something like this, and please refer to our paper for the proof. Second problem is how to pack and unpack the quantized data efficiently. Here is our example of the SIMD-based parallel unpacking on the CPU. The packing process is simply the reverse and it's even easier. Assume a parallelism of 2, and here we need to unpack 8 U in 4 values. In each step, we perform a left shift and a right shift to extract a pair of outputs simultaneously. This way, we can unpack all 8 values in just 4 steps. But there's still an issue. The CPU packs data row by row, so they create an interleaved layout. And when we try to use the GPU for unpacking and computation, each block expects to read in tiles. But the CPU layout doesn't match this. For instance, the first GPU block lists Q2 here, but it ends up being read by the second block instead. To fix this, we designed a unified layout. Each line matches the GPU block size, and inside the tile, data follows the CPU's order. At last, we want to solve the fragmentation problem. In regular training, each activation has a fixed size. Frameworks like PyTorch are good at handling memory allocations and reuse. But with dynamic quantization, the size of each activation can change from one iteration to the next. PyTorch's default memory manager cannot efficiently reuse memory of these different sizes. And over time, that will lead to serious fragmentation. Here, we use a page management system to do that. The key idea is that DAF allocates a contiguous memory block for storing the activation. At runtime, it manages the activations using a page-based index mechanism, which allows for efficient storage and retrieval. We use CPU to do this memory allocation because CPU is fast enough to do that, and the overhead can be hidden by GPU calculation. Here is an example. Imagine we have already stored activations A1, A2, and A3. When A4 comes in, we use a red-black tree to decide based on the importance whether it should be stored. Different quantization algorithm defines importance differently. Suppose we decide to evict A2 here, then A5 arrives. Although the total memory space is sufficient, A5 cannot be stored due to the memory fragmentation. To solve this, we store activations in pages, allowing tensors to be split and stored into long contiguous memory regions. You can find the full details in our paper. And to evaluate the performance, we used 2 different model types. ResNet as the convolutional-based model, robot, and GPT-2 as the transformer-based model. We tested DAF on edge and mobile devices. We compared DAF against 4 baselines: the original, fixed 8 bits, elastic trainer, and ACTNN. The original baseline corresponds to the standard training. Fixed 8 bits stores both the weights and activations as 8-bit. And the elastic trainer and ACTNNs are 2 dynamic activation frameworks. This is the result of the memory saving for ResNet on JSON Xavier. We can see that DAF outperforms other methods in optimizing memory usage while maintaining negligible accuracy loss. The largest improvement is observed on the CIFAR 10. That's because CIFAR 10 is a simple data set where the small resolution allows the quantization technique to achieve a higher level. And this figure shows a comparison of accuracy under different memory budgets. Each point here presents the highest accuracy achievable under a fixed memory constraint. It reflects how different methods perform when memory is limited, especially on edge or mobile devices. And DAF achieves up to 22.9 times memory savings compared to default training. And in the figure, this light blue area shows the best memory savings you can get without DAF. Specifically, that's what's possible with ACTNN. We use 1% accuracy drop as the threshold here. And for the methods like fixed 8-bit, elastic trainer, and original, there's only a single point on the graph. That's because they don't change the actual size of stored activations during training. And this figure shows how accuracy changes when training time is limited, but memory is not. As you can see, DAF speeds up training compared to the default approach, which represents the longest time needed by the original method to finish. Across different platforms, DAF achieves speed up to 3.2. And what's more, compared to fixed 8 bits and elastic trainer, DAF also delivers higher accuracy with the same time budget. To sum up, we introduce DAF is a dynamic activation framework that makes on-device training both scalable and efficient. It supports different dynamic activation quantization strategies and also brings real memory savings and performance gains. Our experiments shows that DAF can reduce memory usage by up to 22.9 and speed up by up to 3.2 on various edge and mobile devices. And that's it. Thank you for your attention.
Okay, thanks Renyuan for the great talk. Now we have a couple minutes for the Q&A sessions. So, okay. If no one have questions, then maybe we just wrap up this part here, and then you can, if you have further questions, then you can talk during the offline.
Okay, thank you.
Okay, thanks again for the presenter.